Okay, let's get started. The next property we're going to discover is the warp weft option. This gives us the possibility to adjust the stiffness based on orientation, allowing a cloth network to stretch more on one axis than another. Now we turn it off, then run the animation and look at the example. I just pinned the top points of the cloth to hang it and animate the collision geometry by bending it on both sides. That's all vellum properties are default. So now let's turn it on and set it up. To use warp weft, we need to provide the UV attribute, so let's create it. For that we will create the UV project node. Put it here. Then jump to the UV view by using space 5 combination. Look, here is the UV projection map. By default it stores it on the vertices. But we can specify points from here. Let's check again. See, it's already stored on the points. So now we have to define the UV name here. Then we can already decrease the warp scale, which will reduce the stiffness only along the U-axis. I also want to put a 0 for the shear scale, which affects the stiffness in the diagonal direction of the UV axis and will prevent us from clearly seeing the effect of the warp and weft. Well, let's see how it will look with these settings. Look, it is now stretches only in one direction, that is it is elongated, but in the direction of width it remains unchanged. Now I propose to do the opposite so that it stretches in the V direction instead of U. We just swap the values between the warp and weft. As you can see, it turned out exactly the opposite. Stiffness is weakened towards the width. Therefore, it does not elongate, but on the contrary becomes wider. To make it more obvious, let's scale down the weft even more and check again. See, the length is almost unchanged, but towards the width, it stretches almost without resistance. Okay, now let's go back to the previous settings. When it is stretched vertically, then we will edit the UV attribute so that only half of the cloth loses its stretch stiffness. To do that, I will use the UV edit node. Let's drop it down. Switch to the UV editor. Then go to point selection mode and select the top half of the points and rotate them to become vertical. Let's also move up a little so as not to overlap them, although this will not affect the simulation in any way. It turns out that the upper and lower half have different stretch stiffness in U and V directions. So let's check what we got. See, the lower half has lost stretch stiffness in the vertical direction, and the upper half has lost stiffness in the horizontal direction. To get the opposite result, we only need to swap the warp and weft values. That's it, we got exactly vice versa. Well, in this example, all the necessary I have already shown, but I prepared another example related to warp weft, so let's switch there. This time, we will use this simple grid in which top points are pinned and it hangs from them. Everything else is by default. Good, now let's turn on the warp weft option, then we will create a UV map. Let's use the UV project node again. To have a correct projection, let's click on Initialize button, then store the UVs on points. See, here it is. Well, let's go to the constraint properties, then give the UV name here and start editing the warp value. Before we zero out the shear scale, let's play and see its effect on the simulation. Look, the shear scale only affects the stiffness in the diagonal directions, which strongly prevents stretching in the vertical direction, taking on most of the stretch resistance. Okay, this time we will also reset it to 0, so it doesn't interfere. There you go, it is already stretched without obstacle in the vertical direction. So now let's make the stretch uneven in the vertical direction. To do this, we're going to distort UVs, and we'll do it with a UV brush node. Let's go to the UV editor, then drag with a brush and distort this uniform map. So now UVs look like this. Okay, let's run the simulation and see what it will give us. Take a look how unevenly now it is stretching along the vertical axis, and it's all due to UV distortion. Now let's swap the values between warp and weft to make the stiffness uneven in the horizontal direction. So it also looks quite interesting. We also can make it stretch unevenly in both directions. We just need to add vertical distortion to the existing ones. First, let's reduce a little more the weft scale and then decrease the warp. Check the result. Look, we have fully anisotropic stretch stiffness in both directions. So I believe we have fully explored the use of warp weft. Now I propose to go further. The next property that we are going to discover is plasticity. For this I also prepared an example file. Let's switch there. Okay, before we enable the plasticity, let's look at the example we'll be using. I pinned all the border points and animated collision geometry, which strongly pushes the cloth and comes back. Everything else is by default. Now I want to draw your attention to the clothes in the most stretched form. Look, the collision geometry stretched it quite strangely. The triangulated mesh is also unevenly distributed. Now I will show you how you can solve these problems, and after that, we will return to plasticity. Let's go to the solver settings and talk about the collision passes. It is the number of collision detection passes to perform. These are interleaved between the constraint iterations. That is now, during the 100 iterations of the constraint, 10 collision detection will be performed, which is not enough to properly handle the collision in such situations. Okay, before we increase this value to improve collision, let's reduce it to make the problem worse, and everything will become clear. See, the result of collisions is much terrible than the previous one, because during 100 iterations of constraint, there is only one collision detection. So now we will increase on the contrary the collision passes and check again. Look, it turns out that now at each iteration, there should be collision detection. Let's check the result. See, this time, we got a very proper collision. Let's go to the frame, where it is stretched as much as possible, and take a close look. You see, that strange shape disappeared entirely, and we also got a very uniform mesh of triangles. So, when you increase the number of collision passes, you have to consider that solver will perform the specified number of collision passes at each substep, which can be quite expensive on simulation speed if you have many substeps. Okay, now let's back to the plasticity option and enable it. As you can see, we are already familiar with the interface. Everything is identical to bend constraint, and the only difference is that instead of bending, it works based on the distance between particles. Plus, there is one additional option that is not in the bending property. For distance constraints, the threshold can either be an absolute distance or be a percentage distance. When this option is checked, this means that the percentage distance is taken into account. A value of 0.1 as a ratio would mean 110% stretching, 90% compression, would cause plastic flow. Okay, now let's check the result. See, where the stretching exceeds a given threshold, plastic flow occurs, as a result of which the stretched areas do not return. Well, let's visualize the stretch plastic flow attribute and look again. We need to adjust a maximum stretch value for this simulation. That's better, let's play again. Now you can clearly see where and how much plasticity has flowed. Good, we will increase the plastic threshold and look again. As you can see, this time, only a small part of the deformation is preserved. Everything else did not exceed the specified threshold and returned. Now let's decently increase the rate value to quickly accept new rest lengths and keep almost all deformation that exceeds the given threshold. Look, due to higher rate values, all the deformations that crossed the threshold were preserved completely. Therefore they are red. Well, now let's on the contrary, decently reduce the rate value and compare. See how a small portion of the deformation that has exceeded the threshold eventually preserved. I think everything is clear with the rate. Now let's look at the case where the threshold works based on the absolute distance. First, let's increase the rate value, then remove this check, and the threshold will take into account the absolute distance. As you can see, nothing happened because now the threshold is equal to 0.5 meters, which in this case is a huge distance. So, let's put a small value and check again. See, we already have stretching that exceeds a given threshold and causes a plastic flow. Well, I think we figured out the difference between the absolute and the percentage distance. Now let's touch the hardening parameter also and move further. I will set the value below 1 to reduce the stretch stiffness during plastic flow. See, the stiffness dropped very low, that's why such an artifact appeared at the end. So, let's increase it a little bit and check again. Notice how the stiffness decreases and contributes to the cloth being extended a little more. Well, let's move on. You can also use the custom point attributes to scale all these three parameters, as well as manipulate them during simulation inside the DOT network, like we did for bend plasticity. All this can be done by the already familiar vellum constraint property node. The only difference is that you have to choose the stretch constraint instead of the bend. Everything else is the same. Here they are. Well, that's probably all I wanted to show with this example. I have prepared another example related to plasticity. Let's quickly walk through it and then move on. So, before we start, let me show you an example. As you have already noticed, we already had a similar example. And this time, we will use it for a different purpose. The cloth stretch decently and then come back, all vellum settings by default. Okay, now let's enable the plasticity and see what happens. See, now it did not shrink like rubber, but retained its elongated state like cellophane. Let's find a frame where it is maximally stretched. Then, we will turn on the stretch plastic flow visualizer and set it up. Fine, let's check it in animation. Please pay attention to the color transformation, because it is an excellent indicator of how quickly the material takes its new rest length. Now let's reduce the rate and watch the color transformation again. Look, there wasn't enough time for it to redden. This means that it has not captured a certain portion of the elongation. If the clothes are held in a stretched state a little longer, it will have time to redden completely, and as a result, the elongated state will be completely preserved. Well, now we decently increase the rate value and watch how the color transforms. Notice how quickly the color turned red. That is, all the elongation is saved immediately. I also want to draw your attention to the fact that not only elongation, but also compression has been preserved, therefore there is a narrowing especially in the middle. Okay, we can already turn off plastic flow visualization, we don't need it anymore. Now I propose to play with the hardening parameter and see what we get. As we set the value below 1, the stretch stiffness decreases where the plastic flow is triggered, therefore, the elongation is much larger than usual. Let's reduce it a little more and have a look again. Now it has already decreased so much that it began to flow down. Okay, now let's do the opposite, set the value above 1, which will increase the stiffness during the plastic flow, but we must also reduce the initial stretch stiffness since it is now as stiff as possible. See, exactly the opposite is happening now. At first, it stretches easily and then quickly gains stiffness and stops. That is, if we further increase the hardening, it will begin to gain stiffness much faster. As it happened now. And the last thing I want to do is reduce it so that it gets stiffer much later and lengthens decently afterward. There you go. Okay, I think we've completely dealt with plasticity, so I propose to end this lesson here. In the next lesson, we will already discover in detail the pin-to-animation types and try to do interesting manipulations by pinning and unpinning points. See you in the next lesson.